Hello everyone, my name is Ashley Goodnight and this is my Reading Week 12 video. This week we covered a third fundamental principle, the angular momentum principle. While our other two physics principles focus on translational motion, the angular momentum principle deals with rotational motion. In order to describe this rotational motion, we use rotational momentum, called angular momentum. This is a vector quantity that is depicted with the symbol L. We also use a net rotational force, called net torque. This is also a vector quantity depicted with the symbol tau. Mirroring the momentum principle, the rate of change of angular momentum tells about the net torque. But let's start from the basics of rotational motion. Rotational motion is often described in relation to a particular rotation axis. The first step is to define your axis. Like your reference frame, you are able to choose what your axis is. Although it can be whatever you'd like, you should choose an axis which makes the math easy. In my high school physics class, we discussed torque. When looking at a force applied a distance from a fixed point, you can test that only the perpendicular component of the force is able to cause a twisting motion. You can also test that the amount of twist is directly related to the distance the force was applied. Taking these observations into account, we can find that torque equals the magnitude of the force perpendicular times the distance from the fixed point. This can be written as tau equals F times sine theta times r. The dimensions of torque are the dimensions of force times a length, so in SI units, torque is the quantity of Newton meters. While some information about torque is a review, we never learned about the alternative interpretation. You can look at torque as equal to force times the distance from a fixed point to the line parallel to the force. You can still use the equation F times R times sine theta, but you think about the force being applied along this line called the line of action. The distance of closest approach of the line of action to the axis, or in other words, the shortest distance from the line of action to the axis, is the component equaling R times sine theta. Other concepts I was not familiar with before are the symbols for the direction of torque. The circle with the X stands for into, while the dot represents out of. To find angular momentum, you need to find the cross product of distance r and the momentum p. The dimensions of the angular momentum are mass times length squared divided by time. With corresponding SI units, this is kilograms meters squared per second. The direction of the angular momentum can be determined by the right-hand rule. Now, for the torque and angular momentum, we discussed the usage of the cross product. In order to find different ways to solve cross products, I went onto an article by Hyperphysics called Vector Products of Vectors, which provided a formula to solve for the cross product in addition to a table-like method discussed in the lectures, as well as further visualizations of the right-hand rule. Speaking of the right-hand rule, my major of electrical engineering has another right-hand rule. With electric fields, you use the right-hand rule to remember the direction of the magnetic forces. If you point your pointer finger in the direction of the positive charge is moving, and then your middle finger in the direction of the magnetic field, your thumb points in the direction of the magnetic force pushing on the moving charge. When you're dealing with negative charges, like moving electrons, the force points in the opposite direction as your thumb. With that, I am concluding my presentation. Thank you everyone for listening. See you all next week.